Here's my solution for the problem 17-38 of the 6 video assignment. So first we're given what the masses are. So M1 is 150 kilos, M2 is 10 kilos. The coefficient of static friction is 0.2, which is unitless. And we know what the distance, the sizes of the block is, which is 1 meter in height and half a meter in width. So we need to determine the maximum force P that can be applied to the handle without causing the crate to slip or tip on the cart. So we can assume that there's no slip within the boundaries of P. So anything larger than what the force we calculate will be, then there will be slip. But anything below that, there won't be. So I drew two schematics. The one on the left shows the whole thing and the coordinate system as well. And on the right side, number 2, it shows only the block itself with 4 forces, one of them being an acceleratory force, and a moment force, all of them going in separate directions. So that coordinate system applies to this as well. And first, we have to find what the force of static friction is. So that's Fs equals mu s multiplied by Fn, which is the normal force. But we don't know what Fn is, so we can do the sum of forces in the y direction, which is may, which, since this is in equilibrium right now, we say that it's 0 equals to Fn minus mg, which is the gravitational force. Simplifying and substituting, we get that Fn is 1,471.5 newtons, or 1.471 kilonewtons. And we can use that to sub in for Fs, and we finally find it. So that's Fs is 294.3 newtons. So we can also use Fs in the summation of forces in the x direction as well. So that's what we're going to do. The summation of forces in the x direction is max. So we only see that there's the force going in the negative direction to our coordinate system, which is Fs, plus the acceleratory force is 150a. So finding for a, subbing everything in, we get 1.962 meters per second squared, excuse me. And now knowing that, we can solve our moment equation as well. So if we look back at the second diagram, we can see that we know what the height in the y direction is of the acceleratory force, because that matters on this. But we don't know what the x direction is, where it starts from. So we need to find what that x is. So that's, once we do the moment forces corresponding to their lengths, we see that it's m1gx equals to m1a, and that's 0.5 y value. So crossing everything over, crossing out things that aren't necessary, crossing out things that divide each other, rather, we see that x is 0.1 meters, or 10 centimeters. So now we know what x is. And now we can find what the sum of forces in the x direction is for the whole schematic, because right now I was finding all of these summations within that second diagram. But in the large diagram where P is involved, it's a little different. So we see that Fx equals 0. So 0 equals to negative P because it's going in the left direction and right is positive, plus M1 plus M2 all multiplied by A. That's the whole diagram that's being included in that acceleration. So we see that P is 313.92 newtons. And in the end, that's all it is.